Uh, Good morning, everyone. My name is Asterios Gavrilidis, and I'm a professor here at the Chemical Engineering Department at University College London. So it's a pleasure to have a chance to talk to you today about an aspect of our work and our research that we have been working on for quite some time. But today, of course, will be a broad overview of this area over the last 20, 30 years. And we'll start, in fact, with a bit of history, with going back all the way to the 16th century. And why do we go to that? We go to that to see how people actually were extracting gold out of gold ore. So you can see here a picture from the book of from Agricola, the Metallica Libri. You can see it's a very old book, 1556. You can see here some stirred tanks, and this is where the gold ore was actually mixed with mercury to extract it, and then it was passed on a filter to extract the mercury which contained the gold. Here, over there on the bottom, you will see a stirrer, and these are the stirrers that were used back in the 16th century, so that we can have a well-mixed conditions inside the stirred tanks. Now, if we fast forward to the 20th century, you will see that there are some similarities. Here are the three tanks that we just saw with a stirrer, and here you can see three tanks over here at the bottom from a chemical plant, which is, this picture was taken in 2002. The difference is not that much, in fact. The similarities are more striking. The difference is the fact that here, of course, these were made by wood, the stirrer tanks, here were made by metals. But if you see the stirrer inside a cartoon of how the reactor will look like in the stirrer here, they look very, very similar. So in that sense, you can see that a lot of what the chemical industry has been using over the last few hundred years has not changed that much. And in fact, these reactors are still being sold and being used, and they're working very nicely. But we would like to see if there is a new technology, considering now that we're in the third millennium, we would like to see if there is a new technology that we can use. And this technology will be the one that we'll talk about today, will be process intensification. So what is process intensification? Process intensification is a strategy for making very large reductions in the size of a chemical plant. So we can make things much smaller, but also we can make them much more efficient. These reductions come from shrinking the size of the individual pieces of equipment, but also by cutting down the number of operations in the chemical process, as we'll see later in some examples. This concept of processification started by Professor Colin Ramshaw, who was initially at ICI. ICI does not exist right now. It was a chemical company based on the north of England initially, but it was an international company as big as it would be the corresponding of BASF today. And he actually suggested this concept. After that, that was back in the 1980s, people in China developed the high-G technology that he actually started talking about in the 90s and maybe a bit later. The Delft University of Technology, together with DSM, worked on structure reactors, developed further the technology, and moved into PI. And after that, it was France who got into the technology. And in fact, maybe about 5 years ago, finally the US started getting into this technology, and they have a big program which is called RAPID. So the processification has the origins about 40 years ago in the UK, but now it is used internationally as a concept for improving chemical plants. Some other type of characteristics of processification is that when we are talking about processification, we're talking about a revolution rather than an evolution. And this is because the change is substantial. We're not talking about decreasing the size by a factor of 10% or 20%. We're talking about decreasing the size by a factor of 1,000%, 10,000%. Another way that to think about processification, which is something that Andrei Stankiewicz is another person who was very much involved in processification from Delft, as I mentioned earlier, used to say, is that processification is basically using less to produce much, much more. I would say also these days it is important also to make not just make more, but also make them more sustainably and more environmentally friendly. So many of the present chemical plants look like that. So this is kind of a virtual excursion of school children in a chemical plant, and the engineer here, you can see, is very proud and showing the school children this chemical plant, and he says this is the biggest unit of its kind, and this is where we are. You can see the big refineries, and this is how they would look like. And they still look like that currently. What we want to do is, in the 21st century, go and change this paradigm and talk about, not about the biggest, but the most efficient, the most sustainable unit of its kind. So you can see now the pictures of the old chemical plant on the walls, and hopefully our chemical plants in the 21st century and beyond will be much more efficient, smaller, and unobtrusive. So this is the new paradigm of process intensification. What are the benefits of processification? And here PI is for processification. The capital operating cost and the capital and the operating costs, hopefully, when we use processification, can reduce by a factor of 20 to 80%. So you can make processes cheaper. We use smaller chemical plants. Very importantly, we can increase the safety. And the safety increases because we decrease the volume. So if you decrease the volume of a reactor of a chemical plant by 10 to 1,000 times, then you have less chemical available. And if there is, even if there is an accident, the impact will not be as high as would be with a standard chemical plant. Energy savings, which are very important, it can be 20 to 80%. Less waste, which means that we have better selectivity to the desired product. And selectivity is a measure of what is the percentage of the raw material is converted to the desired product as compared to the undesired. So we like to operate at 100% selectivity, meaning 100% of the raw material gives 100% of what we desire and zero waste. And there are other aspects which are interesting to managers, which are shorter time to market because they are smaller chemical plants and so forth. These are from a study from the Dutch Energy and Environmental Agency. So these numbers are actually numbers that people have come up based on examples of process intensified plants by that time. What are the barriers to PI? Today, there are still, most of the plants are not intensified, although there are more and more chemical plants, particularly the new ones, which are designed with the processification in mind. One is the investment risk, because these are novel apparatuses and processes, and in some cases it's not proven, and that's why there is some, if people are risk averse in the industry, they would tend to actually use the old equipment. We need more research and development, and this is also what we are doing at UCL and in other chemical engineering departments to better understand and develop these processes so that they can be taken up by industry. The route from lab to the plant is not always available. We develop them, we study them in the universities, but then before industry adopts them, we need to study them, and we need to demonstrate them at pilot plants and a slightly larger scale, not yet at the final scale, but we need to demonstrate them to build confidence in the industry. And this is the major issue, basically, the unfamiliarity by engineers in industry that we will need to make sure we overcome. And here is an example of the chemical industry. This is not from the chemical industry, but this is the same type of mentality you see in this cartoon, where here the soldiers and they have a fight, a battle to fight, and as you can see, they are so engrossed on their own type of urgency to fight the battle that they are not interested in using the new technology that can potentially help them. And processification is not something actually that new. If one looks back on the first industrial revolution, and if you have an old 20-pound node, you can actually find hints of processification on the 20-pound node. This 20-pound node has Adam Smith, which was an economist, who wrote this book in 1776, The Wealth of Nations. And over here, I'm not sure if you can read it, but it says the division of labor in pin manufacturing and the great increase in the quantity of work that results. So Adam Smith, in the book, says that he visited a pin factory which employed 10 men, and these 10 men produced 48,000 pins a day. And he goes on to say that if in this factory, the labor was divided, so each worker did a different task. One of them would be the packaging of the pins. However, if there were 10 workers that did all of the steps themselves, from the initial using of the raw material, creating the pins, all the way to packaging, then in that case, he reckoned that they could produce 20 pins a day. So you can see process intensification in action here, going from 20 pins to 48,000 pins. So this is in fact, how the Industrial Revolution started. And you can see that the concept, which in that case was by division of labor. And of course, pins maybe now are not very much used, but the concept of having a different philosophy of the way that we organize the chemical plants, and that was a chemical plant here. It was can provide an intensified increase the productivity by many orders of magnitude. Currently, the way we can achieve processification is by developing different equipment and developing different methods. And we'll see various examples of reactors. For example, developing a reactor like the spinning disk reactor, the static mixer reactor, monolithic reactor, and microreactors, but also with method using other type of alternative sources like centrifugal fields, help a lot with processification, ultrasound. We would like to use more and more solar energy and electric fields, microwaves. As you know, the chemical industry now is moving away from using as energy vectors oil. They try to use electricity. So this is, in fact, another example of processification. So these are two equations which are very similar. They're very simple, but they give you a very good grasp of why we can intensify processes when we go to the small scale. These equations are, if some of you may have come across this, essentially it's like a Fick's law over here. Here, the Fick's law, rate of mass transfer is surface to volume ratio, the surface of a vessel, external surface over the volume of that vessel, multiplied by a certain proportionality constant, which in this case is the diffusivity, and multiplied by the driving force, which is a gradient of concentration. So the difference in concentration over the difference of distance from a point inside the vessel to the point where we need to have the mass transfer. And this is the same equation here. In that case, it's called the Fourier law, the heat transfer. And these are the stuff that you are learning in chemical engineering. These are fundamental equations of chemical engineering. And it is very, very similar. You can see here, surface to volume ratio. The constant now, it is the thermal conductivity. And the driving force now, it's not a concentration gradient, but it is a temperature gradient. So again, here x is the distance, a is surface area, and v is volume. And this is something that nature has been doing for a long time when nature wants to increase surface to volume ratio. What nature does is decrease the size. And you can see that clearly, simply from geometry. If you take a cylinder and you take the surface of the cylinder, the external surface, p pi dl, over the volume of the cylinder, pi d square L over 4, it would be 4 over d. So as we decrease the diameter of a cylinder from here, from 1 meter to 0.001 meter to 1 millimeter, the surface to volume ratio increases because the diameter is here in the denominator. So the surface to volume ratio goes from 4 to 4,000. And if you remember our equations before, for the mass transfer and heat transfer had A to V, the surface to volume ratio. So you can go from a factor of 4 to 4,000. You can see then the increase by a factor of 1,000 or 1,000,000%. So blood capillary vessels with a diameter of about 10 microns will have a surface to volume ratio of 400,000 square meters per cubic meters, which is huge surface area. An example of a reactor that has been used to intensify processes is the spinning disk reactor, where we have the liquid being fed into a disk which spins. And here the concept that we use is the gravitational force, because we spin the disk, centrifugal forces, because we spin the disk so fast that centrifugal forces throw the liquid towards the side. And you can see here the center of the disk, and the liquid as being thrown on the side, it becomes very, very thin and also create ripples. And these ripples improve the mass transfer, but also improve the mass transfer also because the surface to volume ratio is very high. And I'll try to play a video here to see how this thing works.
The chemical reactor is at the heart of a chemical plant. Reactions are typically performed in large vessels. The spinning disk reactor outperforms conventional reactor equipment, adding unique process controllability. This reactor consists of a stationary casing connected to a motor. The motor drives 3 disks, which rotate at high velocities inside the narrow casing. 2 reactants are fed into the device from the top side and then flow around the rotating disks. The large shear forces provide very efficient mixing of the reactants. This results in high mass transfer rates, allowing reactions to take place in seconds. During the reaction, large amounts of heat are released. Cooling channels are integrated inside the casing to effectively remove this reaction heat. The combination of high mass transfer rates and the temperature control allows reactions to proceed under process-intensified conditions, making the spinning disk reactor unique in terms of efficient, safe, and flexible production.
So that was a description of the spinning disk reactor from a company from Holland who sells them now, Flow ID, Spin ID. And if you noticed, the spinning disk reactor was much smaller as compared to the reactors of the chemical plant. This is another example of a heat exchanger, which is much smaller than a normal heat exchanger. So you can see here an engineer In the context, the engineer here is to give you an idea how big this heat exchanger is that would be used in a chemical plant. And this heat exchanger would be based on cell and cube heat. It would be a cell and cube heat exchanger, meaning that it will have cubes inside, and the cell is the one that you can see. So it will have cubes inside, which will be of the order of maybe 1 to 2 centimeters diameter. This is the new technology from Heatrick, which is a UK company based in Poole. And in this case, you can see now the channels are of the order of a millimeter. So we go from about 2 centimeters to 1 millimeter. And as we just saw before, the surface to volume ratio becomes much larger. And because of that, we can decrease the overall volume that we need. And it is the volume of this printed diffusion bonded, what is called printed circuit heat exchanger, because the technology is similar to the way that we make integrated circuits. It is about 10 times smaller. These diffusion bonded heat exchangers, they can operate at very high pressure, 1000 bar, which in fact the conventional heat exchangers would have trouble operating there. It wouldn't be rated to 1000 bar, and this is because one has much smaller channels. Another example, which we have done also work at UCL for the last maybe 20 years or so, are micro channel reactors. And in this case, we have channels very similar to the heat exchanger that you saw before, which are then even smaller. You can see here 20 to 400 microns. 1 millimeter has exactly 1000 microns, and 100 microns is the thickness of a human hair. So we're talking about here channels which are of the order of size of the human hair. And it is the same concept as before. We have very high heat transfer rates, and because the surface to volume ratio is large. Now, we can intensify this because the heat transfer is very important in the reactions. When a reaction is taking place, we have to take the heat out. So as we increase the reaction rate, we increase the amount of heat produced. So we don't increase the reaction rate beyond the point that we can release the heat, because if we do that, then the reactor is unsafe. So this is one of the limitations of the reactors, of current reactors, particularly for exothermic, highly exothermic reaction, that you don't have enough heat exchange surface area. And that's why these reactors are very efficient and very small, because you have a very good heat transfer surface area, so they can actually run the reactor at high reaction rates, which means a higher temperature, higher pressures, and still safely take the heat out of the reactor. So another example here that we have worked, in fact, with Conley Ramshaw back in the 90s, is an example of a catalytic plate methane reformer. So methane reforming is, steam reforming is the standard technology so far for making hydrogen from methane. And this is how a methane reformer would look like today, the conventional ones. And it will be so large because it will take many, has maybe about 200 cubes, but it will need a lot of space to accommodate the flames to heat the reactor. And in this case, it's an endothermic reaction, which means that we need heat transfer, large heat transfer area to have the heat entering the reactor now to make sure that the reaction takes place. So we came up with the concept of catalytic plate reactor, and we replaced the furnace with a catalytic combustion. And we have plates here. So in one plate, we'll have the reforming reaction, produce the hydrogen. And on the other plate, instead of having the flames, we'll have another catalyst for burning the methane, and in that case, providing the heat. So we can do away then with a big furnace for that. And we showed that we can reduce the volume from 1,600 cubic meter to only 6 cubic meter for the same production of hydrogen. An example from DSM, This is one of the companies which has been involved in processification for many years now, and they replaced this stir tank reactor. These are the same stir tank reactors that we've shown in the very beginning of the talk, very similar in concept as the stir tank reactors from Agricola. In this case, they are metal, and they're about, for this particular chemical, they're of the order of 10 cubic meters. You can see it in the back. So they replaced this reactor with a microchannel reactor, exactly the type of reactor we talked about, plates of alternate plates where you have the reaction taking place on one, and on the other we have the heat exchange taking place. So they were able to go from 10 cubic meters to 3 liters, and this is the reactor they've used. And the capacity was the same, was 1,700 kilograms per hour. This is now an example from Corning, from Daniele Lavritz, who has some numbers here from the stir tank reactor, where the surface that we use for heat exchange is the jacket, which is exactly the external surface area of the reactor. And in that case, the surface to volume ratio, the A over V, is 2.5. And as we go to these channel reactors that we've shown before, we go down to about, we go up to about 800 square meters per cubic meter. And for the reactors, the Corning glass reactors, they go up to 2,500 square meters per cubic meter. So this 2,500 is this term here that we've seen before, A over V. So you can see the A over V becomes from 2.5 to 2,500. So you're increasing this factor by this parameter by a factor of 1,000. But it's not just that, you're increasing also K, the volumetric mass transfer coefficient in this particular case, which is from 10 to the minus 3 to 1.5, because you have thinner layers that the heat transfer has to take place. And in this case, if you particularly also if you have turbulence, then the K becomes much larger, and you have also the driving force. So all these parameters here, not just the A over V is affected by decreasing the size, but you are also affecting the heat transfer coefficient and the driving force. And these are the stuff that you are learning as in chemical engineering, which, by the way, this is the difference between chemical engineering and chemistry. Chemistry will try to intensify the process, to increase the process by increasing the temperature, because this is what the Arrhenius equations tells us, that we can increase the reaction rate by increasing the temperature. But in practice, we will do that up to the point we can take the heat out, as I said before, because if we cannot take the heat out, then it's not safe to operate. And this is the domain of chemical engineer, who needs to design the reactor to do the reaction at scale safely. This is the Corning type of reactors, and I'm sure you have at least one product containing Corning glass. I'm not sure if you're familiar, the Corning Gorilla Glass, and the Corning Gorilla Glass is now found in about 6 billion devices, mobile phones, tablets, and so forth, because it's very strong. So it is the same company, but apart from making glass for computers and screens and so forth, they make also reactors. And this is the reactor they make for a smaller scale, 3 to 15 kilograms per hour. They put more of these units here, which they call the heart-shaped reactor, up maybe 4 times to go to about 200 kilograms per hour. And then this is the way they scale up to a larger size. But if we like to increase the volume, the productivity even more, then we'll have a different approach, which is number up of the reactors. And you can see the number up, which means increasing the size. So you can see here about 50 or so reactors in a rack to increase the productivity. And again, these are the type of things that you learn in chemical engineering. You learn about scale up, and in fact, scale up is traditional chemical engineering domain. But due to processification now, we consider also other approach of increasing productivity, which is the number up concept. This is here an example of how we got rid of the stirrer, and this is the way that the people have dealt with improving the mixing of the Agricola reactors. You remember the stirred mixer? So how do we intensify the mixing of these stirred tank reactors? And the approach of various people was actually to get rid completely of the mixer, the stirrer, and use a static mixer, what is called a static mixer. This is an example from a company called Sulzer, and here it's another example from another company for mixing elements. So if we take this, for example, the Sulzer static mixer, it is like bows which are one after the other, and we have 6 bows here. And what they do is they rotate the fluid one side and then they rotate it the other side. Here is the cross section of how it will look like when you put a dye which is blue in the middle and a white fluid on the side. So you see it's not mixed here. So by rotating and splitting it, you start creating lamella here. You split it in 2, here you split it in 4, here you split it in 8, and you split it in more and more. And you can see here by the end, you have split it in so many layers that eventually, when you reach that point, then the mixing will take place by diffusion. And eventually, whatever you do in the end, the mixing will happen in the end by diffusion. This is the same concept here with this mixer, which instead of twisting, it breaks it up. You can see it's a different design, and there are various static mixer design. And you can see here again at the entrance, you have the blue dye in the middle and the white on the outside, which are broken up and very, very efficiently reach 98% mixing after a component which has a mixer has 8 of these units. So these are the static mixer, which is a very good example of processification because now we can mix things much, much faster. Here's another example of intensified reactor. This is a monolith reactor. And again, there are hundreds of millions, if not billions, of these reactors in the world currently, because this is a monolithic catalyst, which is used for catalytic converters. This is what is on the bottom of all petrol or diesel car. Actually, this is for petrol. For diesel will be different. But all petrol cars have at least one of those, some maybe some of them 2 under the car, and this will be ceramic type of monolith, and this will be a metal monolith. It's the same concept here. These channels that you see are below a millimeter. It's maybe 0.5 millimeters or so. It depends on the type of car that one has, because what we have here is that the catalyst is coated on the walls of this to increase the surface area. And because we're increasing the surface area, essentially we're increasing the A from the AV that we saw before, we increase the productivity so we can increase the amount of noxious gases that we can treat, and that's why we can make it smaller. The reason we use a monolith and not a packed bed, which was the original one, is because of pressure drop, because we don't want to create a pressure drop. And even though maybe 50-year times, this type of monoliths will not be used if we go all to battery cars, but a lot of cars in the developed world, in South America, in India, and so forth, will still be using this type of materials for quite some time. By the way, this type of catalysts are being made. One of the company which makes catalysts is Johnson Matthey, which is based again in the UK. It's a very successful UK international company, which has one of the largest share of the catalytic monolith market. This is a reactor that we developed ourselves at UCL. The CAMOX reactor is a membrane reactor to intensify liquid phase oxidation reactions. So in this case, instead of mixing oxygen with a liquid, to create oxidation products, we use membranes. And here it is, we can see the membrane is this layer which separates the two streams. So this is the membrane over here. This is support layer, so it can operate at higher pressure. There is a catalyst on the bottom because it's a catalytic reaction. So the way it works, it has the oxygen, which is coming as a gas. The reactant is coming as a liquid, and then the oxygen dissolves here through the membrane in the liquid layer and reacts on the catalyst. So this that you see here, the white circles, are not gaseous bubbles, but it is oxygen dissolved inside the liquid. And this is a safe way of doing oxidation because this cannot explode. There is a danger if you have gaseous oxygen with volatiles. If there are sparks, the reactors actually, it is something which is dangerous. So we came up with this concept which can intensify the reaction and also do that in a safe way. Another type of reactor that has been developed by initially in Cambridge, and now there is a company called Nitec which sells this reactor, is oscillating in the north of UK. It is oscillating baffle reactor, and instead of having a mixer, a stirrer over here to mix the reactor, they use an oscillation and baffles inside the reactor, so the fluid goes back and forth, and because there are baffles, the fluids are mixed. There are toroidal vortices being formed, and this creates the mixing. And this has the advantage that one can have a lot of little CSTRs in series, and it's a much simpler design. And because we have what is called a PFR type of arrangement, the volume of this reactor will be much, much less as compared to the volume of 3 or 4 of these reactors if we put them together, or one of these reactors. Because of the concentration profiles in this reactor and the exact details of that. If you join UCL, I'll tell you about it in the 3rd year of your studies. These type of reactors are being used for making pharmaceuticals, and you can see here the particles. Most of the pharmaceuticals are making powder form, and then people create the tablets. And these are the type of like ibuprofen or any type of other pharmaceutical that one can use to create the crystals. Here is another type of particles. Here, in this case, is a calcium carbonate, and they're used as whiteners in paints. And it's a very, very simple concept. It's the helix reactor. So instead of having a straight tube, we coil the reactor, and because of centrifugal forces, we have vortices being created, Dean vortices, and these Dean vortices create better mixing and improve the mass transfer, and you are getting this type of product with a helix reactor, where if one uses a straight tube, one gets this product. Is not very well defined, not very uniform, a small particle size is this product. So clearly this is a better product than that. Now we can also make plastic 3D printed reactors. These are some examples of the 3D printed reactors that we have, that people can make. And the advantages are one can make them very quickly. You can do various designs like this one. You can test very quickly different type of geometries. And this is a different mixer design, which is called split and recombine, which is a very efficient mixer again. You can do it very easily by using 3D printing. This is another coiled reactor, similar to the one you've seen that people have done as 3D, using 3D printing. And we can use, again, as we said, the centrifugal forces here to intensify it. And these type of reactors are coming more and more into, they are still in the stage of research. And in fact, I just gave myself a research project for the 4th year MNs students who need to do, if you join UCL, and most of the departments actually, wherever you go and study chemical engineering, you have to do a research project. So in the 4th year, this year, I gave as a research project to design and make a reactor like that using 3D printer. This type of plastic reactors cannot necessarily take high pressures, high temperatures. So people have started using stainless steel. So they are using metal 3D printers, which are selective SLS printers, which are much more expensive. They are not printers you can buy and use them at home. These are much more expensive machines. But still, the point is that one can make very complicated structures. Here you can see the same type of coiled reactor, but this is a much more complicated structure where the heat exchange is the big coiled tube, a serpentine tube, and the reaction fluid, in fact, is here. The inlet and the outlet are coming here. These are like little tubes coiled around the big tube, and they are split and recombined. These are tricks in order to enhance the mass transfer. Another type of way of increasing, of intensifying is using bubble cavitation. Ultrasonics, because if we apply ultrasound in a fluid which has gas dissolving there, we'll have the bubbles increasing in size and decreasing in size because of the compression and the refraction cycles of the ultrasound. And in transient cavitation, these bubbles eventually will burst, and the bursting of these bubbles can create very high temperatures of the order of 2000 Kelvin or Celsius locally, and also can create the reactive oxygen species and other species radicals that can be very reactive. In our case, we have used that at UCL for creating crystals. Here is our ultrasound probe on top of a tube. And here is a superimposed model. The blue is the model which shows the pressure which can achieve with the ultrasound. You can see the pressure that we can achieve is high exactly at this spot. And this is enough to create the crystals, as I'll show you in a little while. We made crystals of adipic acid, which were this size, which is about 25 microns, while the commercial ones you buy are of the order of 200 microns, 190 microns, much larger. But very importantly, they have a non-uniform size distribution. So this is, again, it's a much better product because smaller size and uniform size is key in all these particular materials for all kinds of reasons, for bioavailability in the gut, for pharmaceuticals, to dissolution inside other chemical reactors and so forth. So this is an example here. Shows it's a high-speed imaging of what happens in that section where we apply the ultrasound. You can see the small particles here. These are the adipic acid crystals that are being formed. And what you see as a fuzzy type of areas, the clouds, are in fact the bubbles which are contracting and bursting, which is not resolved as much because we are looking at, we need to look at 100,000 frames per second to capture this bubble cavitation. But we're looking only 20,000 frames per second here. Yeah, here is an example of a capillary gas liquid separation that we have worked again at UCL, using microcapillaries instead of gravity to separate. So you can see here, this is liquid, the red is liquid, and where it is white is the gas. The size here is about half a centimeter. So it's a very, we magnify that quite a lot to see what is happening. So you have a gas liquid mixture which is coming in, and you can see that the liquid is coming from that side and the gas is coming from that side. And this is because we take advantage of capillary forces to separate the gas and the liquid. This is a much faster separation than gravity if you have large bubbles, because it will take a lot of time to actually separate the bubbles from a mixture. But also, quite interestingly, this type of technology has been developed initially by NASA because they wanted to separate gas and liquid in space. And as you know, in space, there is no gravity, so there is no way they can separate gas and liquid by a gravity separator in space, but you can use this type of separator in space to separate gas and liquid. And we can discuss about why, if you want later on, why would NASA would like to separate gas and liquid in space. This is an example of a whole process, a very successful example of process intensification, which people went from 28 unit operations to 3 by combining the distillation with a catalyst in a single reactive distillation unit, which reduced the energy consumption by 85% and reduced the investment, the whole total investment, by 8%. We are moving on with the Industry 4.0 now to various types of intensified distributed manufacturing units. This is an example of MIT, which has precipitation, crystallization, similar to the one I showed you earlier on, and formulation. Formulation means making the pills. So this unit can make pills of these drugs, diazepam, lidocaine, and diphenhydramine hydrochloride. You can make hundreds of thousands of drugs. So you can see that this can be installed in hospitals, in Africa, as long as there is electricity, or various, maybe even in places where it is difficult to reach, and can make the drug as required. This is a larger version that has been developed by Evonik, the Eco Trainer, where you can see a chemical plant in a shipping container. Here is the control room. Here is the unit's operations, the reactor that we've seen before. And here is the chemicals, the raw materials, and the products. This type of Eco Trainer has been used since the early notice. So this is an example from 2010 from Evonik, who developed it for the production of semiconductor quality hexachlorodisilane, which is used for making silicon chips. They constructed the whole container on site. They put it on the customer site, and after 3 weeks, this plant was able to produce the chemical on spec as expected. So it didn't take years to develop the plant, but it take only 3 weeks to get the production going. This is another example of a nitration chemical plant using silicon nitride reactors, which you can see the scale up and the number of concepts here. A company which makes this is Chemtrix. This company started initially from UK, but then moved to Holland. These reactors are from Chemtrix reactors, which are sold to Pantheon, which use them for, it's a chemical company, and they're using it for nitration reaction. So this is the concept that I said earlier on, that you can see here the various shipping containers that are stored in a big facility, which would be something like the Amazon type of warehouse. The feedstocks provide the various chemicals. They are loaded. They are put here in the containers. The containers are put on the trucks or in ships, and they do the production in some cases on a route while they are going from the warehouse to here is an automotive factory, here is a pharmaceutical factory, here on the ship. So you can have this container operating in principle even when it is on the truck. This is a container that Pfizer is using, has used a few years ago, which this container was designed for continuous tableting, and I'm sure you know Pfizer with the vaccines. So this is a container that goes directly inside a chemical plant, a pharmaceutical chemical plant, which makes tablets for, I'm not sure what type of application was that. So this is I came to the end of my talk. I'm sorry it took a bit more time. I'm happy to stay a bit longer for a few questions, but I will challenge you to look at the process specification aspects in the new 20 banknote. And with that, I think I will came to the end of my talk, and hopefully I demonstrated to you that there is a new technology called process intensification that chemical engineers are very much involved in developing to create better, intensified and more sustainable chemical plants. So with that, I will stop sharing, and I will be happy to answer any questions you may have. Let's see. Is there? There is one question. It says, "Is there will be a limit to processification? If so, how do we know that we've reached the limit? In your opinion, how far further can we go?" The limit is there will be some practical limits, and this will depend on the particular process. For example, if we talked about having very, very small channels, the limit will be the chemical that we're using. If we have fouling and they block, then we cannot go very to use very small channels. We have to use larger channels. So the size of the channels will depend on practical considerations. The temperature, how much temperature, how much we can increase the temperature will depend on the materials that we use. We have to go to more sophisticated material like silicon carbide to increase the temperature we use together with chemical compatibility. So the short answer is that there are limits, but this will depend on the particular process. Decrease in volume. Another question says decrease in volume by a factor of 1,000, 10,000 would inevitably lead to more stricter processing conditions, temperature and pressure, and the need for bolt-on instrumented safety systems. How do you deal with these process safety issues? Actually, these type of systems are intrinsically safer because, as you saw, the heat-rich type of reactor can operate at 1,000 bar. So even if there is something going on in there and there is an explosion, as long as the pressure does not build up more than 1,000 bar, the reactor will survive. But the other reactor that you saw, the other heat exchanger that you saw, which was a cell and tube, that wouldn't survive. So it depends on the process, but in general, intensified processes are safer. You mentioned the barriers to the mass adoption of processification in the process industry. What effective levers, technical, political, and economic, can be leveraged to increase the adoption of PI methods in industry? I move from the classroom and lab to the actual plant. This is a very good question. This is a very insightful question, and you are very correct. The technology is there and is developing, and it has to do with the people in industry who have the vision to take that up, and also have in some cases, the subsistence that we need from industry. So there are research projects, research programs that are being funded, which half of the money comes from industry, half of the money comes from government to, as they say, de-risk the technology. And these are some of the ways that the government, the UK government, and also governments around the world, like the RAPID project I mentioned, government is putting some money in so that they actually convince the industry to study this. And as long as industry is convinced that these processes are they will work at a large scale, because these chemical plants can be expensive, then they will actually invest in that. There is also another advantage I mentioned. This number up concept is another way that people are actually looking at it, and there's an advantage because you don't have to have just one plant making the product that you want, the productivity that you want. You can start build up slowly the scale. So you can build a small chemical plant with one reactor, then add the second reactor, third reactor, and put 100 reactors there. So you can build up the productivity this way. This is another way of de-risking it. Can you speak more about the limitations of PI? I hope I covered some of them, like the fouling that we said before. Some of the limitations are the fact that we're still not sure exactly how they work. We need to understand better how they work. The perceptions of the industry is a big limitation we discussed. Are there any examples of processification of biologics production? I believe, I'm not aware of any, but I expect they may be happening because there is a lot of processification now in the pharmaceutical industry. And as you saw, for example, the Pfizer is getting into that. Various companies are getting big into it, and they are talking about distributed manufacturing. And you can see why distributed manufacturing can be important with the COVID situation, because you can have chemical plants, pharmaceutical plants, which will make the vaccine locally, not necessarily in one facility and then ship all around the world, but this can be made locally. And people are working on that currently. A reactor designed to survive 1,000 bar pressure would be very expensive. What materials of construction will be used and how much they will cost? First of all, not a lot of reaction. This was just an example to show you that they can operate at 1,000 bar. The material that we saw over there will be stainless steel, will be fine. It depends on the pressure, and hastelloy. The reactors, they will be more expensive, but it will be maybe a factor of 10 times more expensive. But then again, it depends of how much you can intensify it, because the reactor will be more expensive, but in the end, you may save in the long term because of the operating costs, because the reactor will not need as much heating, and also will be more efficient. So you will not have to separate the byproducts which are coming out of the reactor. Since methanol is one of the fuels being looked at for the future, especially shipping, and can be reformed to hydrogen for using fuel cells. So is the weight and volume of the reformer per kilowatts expected to reduce in the future so that the methanol powered fuel cell can become practical for larger power operations? Is this easier to reform methanol to hydrogen as compared to reforming biodiesel into methanol? This is a very good question. And in fact, the hydrogen that we saw earlier on, the example was, I talked about making hydrogen in larger scale, but one of the applications that we're looking at was making hydrogen from methanol or from other type of, even from petrol, on board of cars. So you can have a mini reformer on the car to make hydrogen for fuel cell. So people have looked into that, but the economics of that, they were not as attractive, and also it was a complex system. And there is also with a way of other things, with other developments are going on in terms of fuel cells and hydrogen storage. This is not taken off. However, there is a lot of emphasis on hydrogen now, and there are people are looking at intensified plants for creating hydrogen out of methanol. For example, where there are petrol stations. So they would put them in petrol stations, would produce hydrogen locally, either from methanol, or there is also a trend to make them from ammonia, to use them in fuel cells. Because although we're talking about fuel battery cars, there is a big initiative right now, at least in UK and Europe, about hydrogen. Because batteries, you cannot operate big trucks with batteries, it's quite expensive. And hydrogen has various advantages because it is much more dense in energy. So all of this technology of in-processification can provide generators of hydrogen either in the desktop scale or even in the back of the petrol station, all petrol station scale for fueling cars. Can you share the on-demand farm production PI per one more time, or tell us when we can read more about it? I will try to find out a paper, the paper where I picked that up, and Mark, if is that okay, maybe you can send that together with the where people can find the video, the recording. Is that okay?
Yes, I will do that.
So I think these were all the questions, and we came to the end. It is 11 o'clock. So I hope you enjoyed, you learned something, you saw where chemical engineering can help in solving problems that we will have in the future in terms of pharmaceutical production, in terms of energy, and so forth. And if there is anything any other questions that you have, I'll be happy to answer them either offline after the seminar. So thank you very much, everyone, for attending. And as Mark says, the records will be made available soon, which you can watch it again. In the end, I had to go a little bit faster to cover the material that I wanted to cover because I thought it was quite exciting. But as I said, if there are any questions or you would like more additional material that you would like to learn more about it, feel free to get in touch with me. And with that, I let you move on to whatever you have to do next. Thanks very much for attending the seminar. Bye.